So, so if you haven't already, you can go onto the Google Classroom and you can download the updated version. Hang on. Is that the updated version? No, that's not the updated version. Function group. I don't know where the updated version is. Oh wait, it's this one. There we go. Yeah, there we go. So this is the updated version, and you'll see I've put some sort of little index in front of it. So at the beginning of the document, there's all the types of reactions that you need to know. And then also page references in terms of the textbook, which you can find them on. And then what I also updated is I cleaned up the examples a bit. I made them a bit more ordered and a bit more structured. I sized them up nicely and I changed the names and the configurations a bit. So that's basically that. There's an example there. There's an example there. Let's have a look. So what we want to talk about today is the Markovnikov rule. And it's on page 209 in the textbook. It's a little green block in the top, in the bottom left-hand corner. Did anybody read about this yesterday? Or did you come across it? Did anybody have a look at the Markovnikov rule?
Talking about the one with the many isomers.
Something like that, correct. So, yes, say it.
No, the amount, like that triangle. It's not a triangle, but it's the many isomers of the one that you saw that you put on WhatsApp.
Yes and no. No, it's not that. It's not that. That was for fun.
Okay.
That was just for interest sake. That was to do with the branch chain isomers that we did last week. And it's just showing you that the more carbons that you add, the more branch chain isomers you can make. The Markovnikov rule has to do with when you get two different products, what we call the major product and the minor product. And then the question is, which one do we consider the major product and which one do we consider the minor product? And it has to do with these addition reactions where you add something across a double bond, where the two things you're adding to the double bond are slightly different. Also, here's a good example. If you look at what we're adding a H, but we're also adding a bromine. So those two things are different. And what you'll notice here is that if you look at it, the bromine has two options. It can go onto that carbon, or it can go onto that carbon. And both of those are perfectly acceptable. In a real world, you'll probably get a mix of those two products. But when we talk about the major product, we're saying which one of those is going to be made more. So 80%, 20%, 60%, 40%, something along those lines. And the rule that you have to remember is quite straightforward. It's that the major product has the bromine on the carbon with the least number of hydrogens. So if you count over here, the number of hydrogens on this carbon here, I'm going to focus on that carbon, there's only one hydrogen there. Well, and if you look at this carbon on this side, on the right-hand side, there's one hydrogen and there's two hydrogens. So if you highlight the rule again, it has the bromine on the carbon with the least number of hydrogens. So would you agree with me that the middle one would be the major product? Thumbs up. Yep, good. Everyone happy with that? So that's what they mean by Markovnikov selection. In other words, you would get both those two products, but the one on the left-hand side, the 2-bromopropane, would be the so-called major product. Cool. So let's have a look at an example here. Addition of steam to but1-ene. Remember that when we add steam, what we're actually adding is simultaneously an OH and an H. So one is adding an OH and the other one is adding an H. So if you follow the oxygen around, the oxygen can either go onto that carbon or the oxygen can go onto that carbon. Now, since I've drawn it as a skeletal formula, you have to remember that there's hydrogen implied. So you have to remind yourself that there's actually a hydrogen here and that there's actually two hydrogens over here. So if you count that, that's one hydrogen, that's two hydrogens. And if you look at the rule, the major product has the OH on the carbon with the least number of hydrogens, and that's this one over here. Cool. So both those products are possible, but the one on the left-hand side, the butan-2-ol, would be considered the major product. Cool. Everyone happy with that so far?
Yep.
Good. So that's what we mean by Markovnikov selection. So let's have a look here. You have an unfamiliar looking molecule. And remember that you don't need to be scared by unfamiliar molecules. Unfamiliar just means that you probably don't need to know the name of the molecule, but what you do need to do is be able to identify the functional group and how it's going to be converted. So in this case here, I identify the fact that that's an alkene, and I look at what chemical is being added. And I realized that the alkene, and let's call it the hydrogen halide, HX, those two are going to react. So that I know that this is not going to react anywhere else on the rest of that molecule. So I'm safe to assume that it's only going to react with the double bond. Cool. Then if you have a look, you have two options for the bromine. You can add it to the, hang on. You can add it to this carbon over here in the middle, or you can add it to that carbon on the end there. But then you have to remember that we have hidden hydrogens. So we have to draw this hydrogen over here. That's hydrogen 1. And then on this carbon, we actually have two hidden hydrogens that look like that. And then the selection rule says that the major product, the major product, oh, it isn't written explicitly here, but you know the rule now. The major product is the one that has fewer H's. So it's bonded to the carbon with a fewer number of H's in that case. So you can ignore the rest of the molecule. You don't have to focus on anything else. Don't worry about the fact that there's a benzene ring and a chlorine there. You just focus on the double bond, and you focus on what you're adding to the double bond. So ignore the rest of the molecule, and you wouldn't be able to expect it to name this molecule. Talk to me, sorry.
So the bromine will be rather on carbon 2 than carbon 1, because
100%.
at the end carbon 1 will have two other hydrogens, and then carbon 1 will only have the one other hydrogen.
Correct, 100%. And if you remember it that way, what you said is absolutely perfect the way you said it, because if it has the option to be on the end of a molecule or somewhere in the middle of a molecule, it'll always choose to be somewhere in the middle because there's fewer hydrogens in the middle. And I think Angelica said it somewhere along the line long ago that in the middle, it's always CH2, whereas on the end, it's always CH3. So there's always fewer hydrogens in the middle because you have more carbon-carbon bonds. Cool. So what you said is absolutely perfect. That's a very good way of remembering it. It'll probably rather go to carbon 2 than onto carbon 1 because there's more hydrogens on the end carbon. Cool. So let's play around with this a little bit. Let's just make up a few things. So have a pen and paper out, and then what you're going to do is you're going to draw the major product and you're going to draw the minor product, and then not so much explain it, but just rationalize to yourself which one, why is it not the major or minor product. Okay, somebody give me a number of carbons.
5.
5, okay, so I'm going to draw it slightly different to what you're probably expecting. I'm going to do it like that. And then give me a position of the double bond. I'll write it for you 1, 2, 3, 4, between 1 and 2, between 2 and 3, or between 3 and 4.
2 and 3.
Cool, so you want the double bond between 2 and 3, so you put that there. And then do you want any additional add-ons? Would you like to put anything else in the molecule in terms of chlorines, bromines, hydrogens, whatever? All the hydrogens are implied, so anything else?
Let's add a bromine on carbon 1.
Cool, so let's add a bromine over there just for fun. Cool, and then what would you like to react it with? Anything you want, you can choose water, halide, hydrogen, or a bromine, for example.
Water.
Good stuff, because then you're going to get asymmetrical addition. And remember that it has to be water in terms of gas, it has to be steam. Okay, cool. So I'll give you 3 to 4 minutes quickly. Just draw both products and then tell me which is the major product and which is the minor product. Cool. I'm going to pause quickly. Cool. So I'll give you 3 minutes and then let's go. So it's going to be difficult for you to draw it, so I'll just draw it over here. So stick with the basic structure. Don't change anything about the molecule, and literally just eliminate the double bond. So all I'm going to do is redraw the structure, and then I'm going to eliminate the double bond. And then I'm going to ask myself, I have to add an OH and I have to add an H. So just randomly, I'll put an OH here, and I'll add an H there. Strictly speaking, I don't need to add that H there because it's implied. You'll see that if I take it away, it's assumed that there's a hydrogen there in any case because it's a skeletal structure. So that's one possible option. And then the other possible option is keep the bromine where it is, keep that bond where it is, and then add the OH over here. And then obviously the hydrogen would be added here, but I don't really need to add that because it's a skeletal structure. Cool. And then the question is, which is the major product and which is the minor product? The top one or the bottom one?
The top is the major.
Cool. Who agrees with Gloria?
Wait.
Yeah,
So
Angelicus.
I'm confused.
I'm not saying she's right. I'm just asking who agrees with her. You don't have to agree.
No, I know, but what is the hydrogen on? Isn't there 2 carbons on the end there?
It is, but remember it's a skeletal structure, so you have to realize that this bond here goes to a CH3, and then this bond here goes to a CH3. That's implied in the skeletal formula, so it's implicit. So you don't have to draw those there in a skeletal formula. But yes, if you wanted to, you could put those CH3s just to remind yourself that they are carbons. Cool. So let's focus on the 2 carbons that we added to. So let's have a look at them. Let's have a look at this carbon. I added the OH to that carbon and I added the OH to that carbon. Now, because it's a skeletal formula, you have to dig deep and you have to think to yourself, what is missing on that carbon that I haven't drawn? There's 1 hydrogen there. Cool. Now, on this carbon on the bottom, I'm just going to quickly ring it for you. Are there any hydrogens at all bonded to that carbon?
No.
Yeah, so if you look at it, I'm going to draw an arrow pointing it. There's actually no H's at all. No H's. Because if you look at what carbon is bonded to, it's bonded to a C at the bottom, a C on the right, an OH, and it's bonded to another C. So it doesn't have space for any hydrogens. Also, remember, carbon can only have 4 bonds, and if it's bonded to 4 things already, there's no space for H's. Cool. And then, Gloria, would you like to change your mind?
No.
So we want the product where the OH is bonded to the carbon with the fewest number of hydrogens. So look at the
that's
highlighted.
the major.
Correct. So which is the major
Okay.
one?
The bottom one.
The bottom one is the major product. Correct. So maybe you just got it the other way around, but that's fine.
Yeah.
So it could just be could be a matter of confusion. So that's what we would end up with. Major product at the bottom and minor product at the top. And that's why it's so important, guys, if you practice your skeletal formulas and if you practice identifying skeletal formulas, not identifying them, if you play with the skeletal formulas, it's very important to remember that there's hidden hydrogen. So I remember listening to one of my videos and I heard Nico talking and I heard him say in the background, but how can there be 4 things bonded to the carbon when it's only bonded to 2 things? And the reason is because in a skeletal formula, we omit the hydrogens. We just forget to draw them for simplicity. Okay, so let's take that same molecule. And then instead of adding water, let's add chlorine or bromine or something like that. Also take the same one. And this time we're just going to add Cl2. Cool, I'll give you, this one shouldn't take more than a minute or so. I'll give you a minute quickly, draw the 2 products or draw as many products as you think there are for this. So draw as many products as you think there are. Okay, so how many products did you get, Stefan? Or anybody, sorry, not just Stefan, how many products did you get?
One.
Yeah, so strictly speaking, there's only 1 product. So if you ignore all sorts of other complicated stuff, and if you redraw that, the bromine stays where it is. We break the double bond, so we get rid of that. And then the question is, where can we put the 2 chlorines? And they can't go on the same atom. So they can't go on the same carbon atom. They have to go on opposite ends of the double bond. So you can get the chlorine here and you can get the chlorine there. And there's no other way you can add that. You can't add those two chlorines to any other atoms, any other carbon atoms. What you will get is what's called a stereoisomer. You'll get what's called a chiral center, and that's a whole different kettle of fish, and we don't want to go there for this lesson. So there's only one product here. One structural product. I'm going to say structural now, and we'll see what that means later. One structural product. Cool. So what you don't end up with is something like this, for example, where you have two chlorines on the same atom. So I'll highlight this in red, and I'll say no, none of that. So none of that. Okay, so in terms of Markovnikov selection, what is one of the prerequisites to have dual products or to have multiple products? What has to be, what is a prerequisite in order to get two different products? In your own words, just say it in your own words.
They should be like different types of elements. Since these are chlorine, and the chlorine, it's kind of the same, but
Correct.
if it was maybe an OH and an
Exact,
H.
and an H, exactly. So like in this case over here, I'll write it for you so that you can see it. If we break that apart, we can say that the hydrogen is actually that and that. So you're absolutely correct. We have two different things to add to the double bond. Whereas if you broke apart chlorine, you've literally just got one chlorine atom and another chlorine atom, and they're basically identical. So that's a prerequisite for Markovnikov selection. And then there's another interesting way to look at this is if you have something like this. So this is a little bit more difficult to see because you have to have a little bit of an imagination. But would you agree with me that the left-hand side of the molecule and the right-hand side are more or less the same? So if I draw a mirror down the middle here, would you agree with me that if I drew some sort of arbitrary point in the middle, there's rotational symmetry about that point? So if I rotated about this point over here, if I rotated it, that side would look identical to that side in terms of rotational symmetry. It's a bit difficult to see because you have to have a very visual imagination. So what I'm saying is if we add two different products to this, so if we add, let's say, HBr, you're going to break the double bond and you can put the H there and you can put the Br there, or you can break the double bond and you can put the Br there and the H there. And what can you tell me about those two products in terms of their structure and or their formula and or their name?
Aren't they the same?
It's exactly the same molecule, correct? It's just drawn differently. So you can actually take the bottom one and you can rotate it to get the top one. I haven't figured out how to rotate objects in this program yet. But you could literally take the bottom one, flip it upside down, and you would get the top one. So play with that, draw it for yourself, draw it on a piece of paper, and then literally take this entire molecule and flip it around. And what you'll end up with is the one at the top here. And this is why you should play around with these things. This is why it's so important, not just to look for questions and look for exam type papers and stuff. The important thing is to play with this and see what is possible and what is not possible. And what you'll end up with is a set of rules that you kind of come up with on your own. Cool. So in this case, what is a prerequisite to have Markovnikov dual products? Why did we not get a dual product here? What was unique about this? So why based on this?
Because it's symmetrical.
Symmetrical, correct. So we have symmetry in the molecule. Cool. The left-hand side of the molecule is exactly the same as the right-hand side in terms of the double bond symmetry. Cool. So you have to think about that. I know it might be a bit difficult. It's a very visual topic. It's one of those things where when you come to class and you play with the modeling kits and stuff, you'll see it firsthand. But the best thing to do is just to practice with it and draw like as many structures as possible and see what you can come up with. Cool, everyone happy with that? Any questions so far?
Sure. So for it to have multiple products, the molecule has to be like non-superimposed, right?
You're using big words that are
I read this in the textbook.
yeah.
You mirror it and then you can't rotate it back to the same thing.
Correct. But it's too technical now because we're not worrying about mirror isomers and all sorts of other stuff. We're literally just saying that the left-hand side of the molecule looks exactly the same as the right-hand side of the molecule. So I'll give you an example and you can decide for yourself. So let's ask, is this molecule symmetrical? Put the double bond there, and then I'll draw the mirror for you so that you can see it. Would that molecule be symmetrical left to right?
No.
Kind of.
No, because if you look at it on the right-hand side, there's two carbons. There's two carbons here, and on the left-hand side, there's three carbons. So by just looking at that, forgetting about how it's drawn and all sorts of other things, there's more carbon on the left than there is on the right. So that's not symmetrical. So that is not symmetrical. And when I mean symmetrical, don't overthink the word. It's just basically saying, is the left-hand side of the molecule exactly the same as the right-hand side of the molecule? Without going too far into other concepts and other considerations, we'll have a look at something like this. Put the double bond there. And then put a chlorine atom here and a chlorine atom there. Cool, and then draw the mirror down the middle. Cool. Is that symmetrical about the center carbon or the double bond?
Yes.
Yes, that would be symmetrical because if you count from the first carbon, sorry, let's not do that in that color. Let's do it in a darker color so the YouTubers can see it. There's this carbon, which is the same as that carbon, so C1. There's this carbon C2, which is the same as this carbon C2. And there's this carbon here, which is the same as that carbon there. So if you were going to add something like HBr to this, you would end up with the same product that would just be rotated. But I'll leave you to play with that. I don't want to show you that example. I want you to go home and I want you to think about that. So add whatever you want to this molecule and see if you can make two different products, yes or no. Cool. Any questions so far? No, good. Okay, so I'm gonna go away from the iPad for a second, and I wanna upload the textbook. So I need to share the textbook, which I have on the computer, luckily, and I want to show you quickly what I want you to read through before tomorrow. Wait, hang on. Where's my textbook? There's my textbook. Oh, I can scroll through the index. That one, okay, and then I'm gonna share the textbook with you, screen share, textbook, here we go. Okay, so we're more or less in this chapter over here. If you page through it, you'll notice that there's sources of alkanes, which is crude oil, which we talked about, then cracking, combustion, all that nonsense. The addition of halogens to alkanes with the UV light, that's all there. And then it talks about the alkenes, and then we talk about the addition reactions. We've talked about water, steam, halogens, etc. And then this is in the notes, this first topic here, the mild oxidation with potassium permanganate. You can read about it in the textbook or you can read about it in the note. But what I want you to do is I want you to have a look carefully at the hot concentrated manganate. So I want you to look at this example over here in the textbook. Where is draw? What I want you to do is look at these examples over here, because this one is slightly more complicated. This one's not as simple as I'm going to add something to the double bond and it's going to form one product. What you're going to do is you're actually going to break the double bond and you're going to form multiple products. And what product you form depends on what you start with. So you've got to go and analyze that. But what I want you to do is I want you to make sure that when you read the next page, I want you to realize that everything that's said on the next page, in terms of these numbers over here, these numbers here, 1, 2, and 3, are directly related to the 1, 2, and 3 on the previous page. So I'll write that here so that you can remember that. It's connect to 1, 2, 3 on previous page. And then what I want you to realize is that on the one side, they've given you structural, and on the one side, they've given you skeletal. So on this page here, you have structural formulas, on this page, and then you have skeletal on previous page. And what I want you to do is I want you to draw them side by side. So I want you to have your book out with you, and I want you to basically take those 2 pages and put them into one page so that you can see it for yourself. Also, make sure that you understand the conversion between the skeletal formula on the previous page and the structural formula on this page. Any questions? Oh, good. So I'll quickly clear the drawings and I'll go back to the previous page. If you look at the previous page, what you have on this page here are skeletal formulas. So these are here at the bottom. These are skeletal formulas. And remember, R groups, like you do in biology, an R group can literally just mean anything. So R groups, in this case, R is any other group. But in this case, let's say in this case, specifically start with carbon. In other words, whatever is attached to an R group, I'll point it out here quickly. If you take an arrow, if I point to this R group over here, what I'm saying is that the first point of attachment there is a carbon. So it's a carbon, but it's connected to anything else. And then you can carry on with the rest of the molecule, and that could be anything you want it to be. But the first point of attachment in the R group is a carbon. So if you look at another example over here, this R1 and that R2, the first point of attachment here is going to be a carbon, and the first point of attachment there is going to be a carbon. And then the rest of the molecule is irrelevant, it's not important. So you could end up literally just drawing anything random on this side here as the rest of the molecule, the rest of the molecule there. So if that was a bit too much to swallow, what I would advise is basically just rewatch the video on YouTube and then make sure that you follow those steps again if you can. Good. Any questions? We've got like 30 seconds left and it's going to cut us off. Okay, so two things to do. Play around with your asymmetrical addition. See what you can come up with in terms of rules. And then the second thing is cold dilute oxidation and hot concentrated oxidation. Good. I'll see the rest of you in physics. Otherwise, see you tomorrow. Bye, guys.
Bye, sir. See you later.
See you later.
Bye, sir.
Bye, sir.
Bye, guys.